Okay, so I wanted to work a couple triangle problems because they're the whole reason why we've been learning trig. So, first one says that you've got a ladder that's leaning up against a house. So I'll draw this little picture here. We'll say this thing here is our house. We don't see the whole thing, we're just going to see the part of it that the ladder is leaning up against. We're told that the ladder is 5 meters long, and that the point it's leaning up against the house at is 4 meters above the ground. And what we want to find here, we're assuming that the house is built correctly and that this is a perpendicular intersection here. We want to find the angle that the ladder is sitting at. So how do I do that? Well, I know it's a right triangle, and I'm probably going to use that right triangle trig stuff, the sine and cosine and tangent. So I need to know what those represent. So a long time ago you were probably told SOHCAHTOA, or some old hippie caught another hippie tripping on acid, or something to help you memorize what the letters are. So we know that sine, for example, is opposite over hypotenuse. We know that cosine is adjacent over hypotenuse, and we know that tangent is opposite over adjacent. So looking at our picture here, what do we know about this angle theta? Well, we don't know the adjacent. That would be this side here. We don't know what that is. We could quickly figure it out with the Pythagorean theorem, but we don't need it. So we do know the opposite, and we know the hypotenuse. So that would be the sine function that we would use. So we know that the sine of angle theta is 4/5. It's 4/5. Opposite over hypotenuse. So I want to find what theta is. I don't really care that the sine of theta is 4/5. I want to know what is angle theta. So I have to get rid of this sine business. So unfortunately this is not sine times angle theta, it's the sine of angle theta. So I need an inverse function, where sine is a function of theta. I need an inverse function to get rid of it. Turns out it's just sine inverse. So if I take the sine inverse of both sides of my problem here, of my equation, well, sine inverse of sine of theta would just be theta. The inverse cancel each other out. And the sine inverse of 4/5, well, I don't know what that is off the top of my head, but I can figure it out pretty quick using my handy dandy calculator. So I want to find, oh, you didn't see that. I hadn't already solved this problem. Shh, don't tell anybody. We want to first be sure that we're in degree mode if we want to find a degree answer. So mode, make sure it says degree. I'm using a TI-83 plus. I don't really think it's a plus and it's a lie. It's a TI-83. So we want to do the inverse sine, which is here above the sine key. So I'll press second inverse sine. 4/5, and I press enter, because it'll be 53.13 degrees. So this angle here is 53.13 degrees, and I've solved my question. There's my answer right there, in all its beautiful glory. So that was a ladder question successfully solved, but not all the problems we'll solve in trig have to do with a right triangle. Turns out, if you were awake in class, which I hope you were, we actually talked about the law of sines and the law of cosines, and I proved those for you. So I'll just write them down here to refresh your brain. I talked about how the sine of A over A is equal to the sine of big B over little b, to the sine of big C over C. So we call this one here the law of sines, where the capital letters here represent angles and the lowercase letters represent sides of the triangle ABC. So little a, little b, little c. So this is just any triangle. It's very generic. It's not referring to a right triangle in particular, or any triangle you want it to be. law of sines will work. So I did a proof in class. If you're deeply curious to see that proof again, just let me know and I'll show you. That's the law of sines. We also have the law of cosines, which will also work for any triangle you got. So any triangle you want to use it on, law of cosines will work. So I'm going to use the one with B. It doesn't really matter which version you use, because we could just relabel our triangle any way we wanted to. So you might have got the impression that there are more equations. There's also one that starts with an a squared equals b squared plus c squared minus 2bc cosine of a, and then also one that starts with a c. So again, all I'm really doing here is shifting the letters around. It's voodoo magic, you might say. There's no tricks. It's just depending on which angle you're looking at. So basically, I could take this same triangle here and relabel it BAC. You'd be looking at a different formula. They all say the exact same thing. You might notice, if you know a little bit about cosine, when the angle we're looking at is 90 degrees, well, cosine of 90 degrees is 0, so this whole term will cancel out. So when you have a 90-degree angle in there, this whole term cancels out, and all you get is something that should look familiar. It's the Pythagorean theorem. We generally look at it using this form here. But that's another way to prove the Pythagorean theorem, is to look at the law of cosines, where angle C is 90 degrees. In other words, where you'd have a right triangle. So I'm going to use these equations to actually solve at least one triangle. I'm just going to make one up here. Let's see, A, B, C, D, E, F, G. If you want to do that, just sing the alphabet song. And a handy trick here is, instead of filling in the triangle itself, I like to make myself a little table. You don't have to do this, but it really is helpful, I think, especially if you're confused on which law to use. So I've got little a, little b, little c, and then directly across from them, big A, big B, and big C. So I don't know, let's say that I know angle A is 17 degrees, and angle B is, I don't know, 72 degrees. And I know that, let's say side B is, I don't know, 15 meters long. Just making up some numbers. So I know three things here. I know that big B is 72 degrees, big A 17 degrees, and little b is 15 meters. So the purpose of drawing this little table here is it helps us to visualize that we have a pair. You know, both little b and big B. So anytime you see a pair like that, you can use the law of sines. So in other words, we'll know that the sine of big B over little b is equal to the sine of big A, the other value we know, over little a. So now I have a proportion here I've set up, and I can solve it for little a. I'm going to cross multiply to do that. So a times the sine of 72 degrees will equal 15 times the sine of 17 degrees. And then divide both sides by the sine of 72. To the a will be 15 sine of 17 degrees over the sine of 72 degrees. I'm going to type that into my calculator and see what it equals. Again, be sure you're in degree mode anytime you have trig functions using degrees. So 15 sine of 17 divided by sine of 72. And voila, I get that side A must be 4.61 units long, and that would be in meters. So I know that A is 4.61 meters. 4.61 meters. I'll erase my work here. And the only thing I like to find is little c and big C. So notice I know two of the angles here in this triangle, and I also know that there are three angles in a triangle, hence triangle. So those three angles in a triangle have to add up to 180. So 180 minus the 72 I've got for angle B, minus the 17 for angle A, should give me what angle C is. So 180 minus 72 is 108. Minus 17 from that, I get 91 degrees. Hopefully I did that correctly. Maybe I feel really dumb if I made a silly mistake there. So we'll say 91. Checking my math. Yeah, that looks good. 91 degrees. I agree with that. So I know that angle C now is 91 degrees. It's almost a right triangle. Almost. But almost only counts in horseshoes and hand grenades. So I now know angle C, and I can use the law of sines again to find little c. So I know sine of big C over little c is sine of, and I'll use B again, sine of 72 over 15. If I cross multiply and solve for C, I'll see that it's 15 sine of 91 over the sine of 72. So I kind of skipped a step there. If you want to verify that I did that correctly, you can pause the video and do your multiplication just to make sure. Keep me honest. So 15 sine of 91 divided by sine of 72. It will be 15.769. So C is 15.7695. I don't want to round up, so I'll put another decimal there so you can see what I typed in. Looks just like that. Fantastic, right? Yeah, so now, and that's in meters. Be really careful about your units. They're super important. So I've solved everything on the triangle, only knowing 3 pieces. And you can do that, again, anytime you know a pair, you can use the law of sines. But you won't always know a pair. Sometimes you'll know everything but a pair. So, let's say, for example, again, we've got that triangle ABC, and this time I know that maybe this is 5, and this is 9, and this is 13. I know 3 of the sides, and I want to solve for the angles. So let's start with angle C here, if I wanted to find that. Well, it's the opposite of that, which would be 5, and I'm going to square it. So I'll show my work here. 5 squared would be the other 2 sides added together after they're squared, minus 2 times one side times the other side times the cosine of C. So 9 squared is 81 plus 169 minus, I don't know that one, 18 times 13 minus 2, 34 cosine of C. Remind me to tell you guys about a calculator I saw. It's really awesome. So, you know, just going through here and solving for the numbers. We're going to move everything to the same side. Minus, or not move everything. We'll move the 81 and the 169 over. We'll have negative 225 equals negative 234 cosine of C. So we're going to divide by this negative 234 there. And I come out with 0.9615384,615 equals the cosine of C. And again, like we saw just a second ago, getting rid of sine, we're going to use the inverse cosine of both sides. So the inverse cosine of that answer we just got should give us our angle measure. So angle C is 15.942. So big C is 15.942 degrees. And once I've got one of those angles, I don't have to do the law of cosines again. I could just do the law of sines instead. Now that I know an angle, so I'd like to say sine 15.942 over 5 is the sine of, let's say, angle A over 9, and I'd cross multiply again and try to solve for A, and then I'd use my knowledge that there are 180 degrees in a triangle to get the last angle. So another scenario where you would use the law of cosines is when you know, instead of side, 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 maybe you know side, angle, side. So that's also a law of cosines problem. So practice some of those, see what you come up with, ask me questions if you need it, and